during which we have a gather.town link where you're welcome to join for socializing. And then we'll resume later on at, I think, noon California time for the third talk. Yes, that will be Stefan. So that's the plan. But otherwise, let's go ahead with Elaine's talk. Thank you very much for being here.
Yeah, thanks so much for inviting me. I'm obviously very happy to virtually be here. I guess this morning when I was teaching my class, one of my students made fun of me with this comic. So I'll let you look at it and figure out what you need to do. Okay, so I'd like to talk about a fun topic, essentially blockchain-inspired protocols where game theory meets crypto. And again, like Zoom talks are not like in person. So if you have questions, like don't wait till the very end, just like interrupt me and ask. The more interactive, the better. Okay, so I'm going to begin with a motivating example that comes from like a true personal experience. I guess this is not uncommon in the crypto community. Like you write a paper and you discover that there's a concurrent paper that has exactly the same result. This happened to me a couple of times. In fact, it happened to me to my first ever crypto paper when I was still a grad student. And then it happened again in 2013. And this time, the two papers even have had exactly the same title. So turns out both papers were submitted to Eurocrypt 14, and then the program committee decided to recommend hard merge. So now the most challenging question is, we have to decide who to present the paper. And how do we do that? Okay, I mean, of course, a Strongman solution is for me and Shafi, who's co-author of the other paper, to wrestle it out. But, we are cryptographers, so we can find a more civil solution. So why not just run a coin toss protocol, right? In fact, this is what we actually did. So coin toss was first proposed in Blum's elegant paper back in 1983. And the way it works is the following. So both Shafi and I send a commitment to, let's say, some blockchain. You can think of it as a public bulletin board or like a broadcast channel. And then we basically both open our bits and we take the XOR of the two bits. In this case, the XOR is 1. So my preference is 1, Shafi prefers 0. So I win in this case, right? This is also what happened. Our group presented the paper. Okay, so I may be concerned that Shafi is malicious. Like, let's say she sees that I have opened the commitment and now she already knows she's going to lose, right? So maybe she'll just abort from the protocol. And then in this case, what do we do? So we can just say, if you abort, you forfeit. You automatically lose, and then I win anyway. So this was just basically Blum's idea. And as I said, this is called a coin toss protocol. It has two requirements. First, correctness is very natural, right? So if both parties run the protocol honestly, then the outcome has to be a random coin. And then we also want fairness. And the standard line of work on multi-party computation has a very stringent notion of fairness. I will call it strong fairness. And this stringent notion requires that even if Shafi aborts, I must nonetheless output a completely unbiased coin. And unfortunately, this is known to be impossible in the two-party setting or in the multi-party setting with dishonest majority. And this was like a famous law bound by Cleave back in 1986. I won't go into the details here, but so it may seem like I'm contradicting myself because, if there's a lower bound, how can Blum's coin toss work? And the key observation here is that Blum's protocol actually achieves a strictly weaker notion of fairness. In this talk, I will call it game theoretic fairness. So in the protocol we've seen, it's not like Shafi cannot bias the coin, right? She can bias the coin, but only in the direction that hurts herself and benefits me. So essentially, we can imagine the players are rational and they care about maximizing some utility function. And fairness or game theoretic security requires that Shafi, whatever she does, she cannot benefit herself or hurt me by deviating from the honest protocol. So in other words, another way to look at this is that Shafi's best response is just to play honestly. It doesn't help her anyhow, even if she deviated. And thus honest behavior is the equilibrium state. Okay, so Blum's protocol achieves game theoretic fairness in a two-party setting. And of course, a very natural question is, can we achieve game theoretic coin toss in the multi-party setting? So imagine we now have n parties. And so, of course, at this moment, it's not clear what the formulation is. I'm going to ask you to hold that thought. And I'll explain in a little bit. And before that, I just want to mention there are like a couple trivial solutions that we want to rule out, right? Under very strong assumptions. Let's say if we are willing to assume honest majority, then a solution to this problem is known. Essentially, we know how to achieve constant round honest majority MPC in general, in constant number of rounds, right? So strong fairness, in some sense, is the best one can hope for because it gives perfect unbiasedness. But in a blockchain setting, like oftentimes, let's say we are playing lottery with the smart contracts, it's not too reasonable to assume honest majority because these players, they're just pseudonyms and anyone can make up arbitrarily many pseudonyms or public keys and participate as many players. So it may well be that 99% of the players are controlled by one entity. Okay, of course, another trivial solution is essentially just to assume the problem away. Like if we can have a trusted setup that can choose like a random seed for us, then the problem kind of just goes away. Of course, in a blockchain type setting, oftentimes we want fully decentralized. We don't want to trust any single party. And oftentimes also, we want this coin to be unpredictable too. Like we don't just want to toss a coin a priori and then it wouldn't be unpredictable. So with this in mind, let me refine the problem statement, right? So I'm asking, assume corrupt majority and no trusted setup. In the plain model, can we have game theoretic fair coin toss in the multi-party setting? So when we first started working on this, we discovered that this question actually surprisingly hasn't been considered in the literature at all. Like, even though if you think about the multi-party computation, the MPC line of work, it started with Blum's coin toss, which achieves game theoretic security. But then subsequently, like all the work on MPC, they considered the strong notion of fairness. Okay. So as I will explain later, actually, even how to formulate the problem is pretty challenging and different formulations can lead to different feasibility results. Okay, so now suppose we can indeed achieve n-party coin toss with game theoretic fairness. The next question we may care about is the complexity of such protocols. So for instance, we can ask about the round complexity of such protocols. Okay, so without further ado, to understand an n-party game theoretic coin toss, we first have to define the problem. There are two different formulations that are very natural. And in this talk, I'm going to actually focus on the second one, but I just want to mention the first one very quickly because then you can see like how different formulation can lead to like wildly different results. So in the first formulation, you can think of it as a binary roulette. Let's say n players, they each place a bet on either 0 or 1. And then you toss the coin, and if the coin agrees with your bet, you win, right? And then suppose like everyone puts in some 1 ether as the bet, and then we can just divide the pot among the winners. And then the second formulation is more like lottery or leader election. So we have n players and we are tossing an n-way coin. We want to elect a single winner and the winner takes the whole pot. So what we discover is like, essentially for the first notion, we can prove broad impossibility results for several natural game theoretic notions. And what's interesting here is that we find that like even how to define game theoretic fairness is not so clear. Like we actually came up with several definitions. They're different in the n-party setting, but when we degenerate to the two-party setting, they are kind of the same as they are the same as Blum's notion essentially. Okay, so as I said in this talk, I just want to focus on the second notion, and so what I want to mention is, without loss of generality, we can assume like a simple utility function. So let's just assume the winner has utility 1 and everyone has utility 0, right? Winner, I mean, in lottery, maybe winner takes the whole pot, but we can always just rescale it to 1. So this leader election problem actually has a lot of applications in decentralized blockchain smart contract contexts. So for example, imagine there's a smart contract and it's looking for service providers to provide some service, like let's say verifiable computation service. And the service provider is like elected at random from some pool. And in exchange for providing the service, you'll get some reward. So everyone's like eager to be elected and, you know, make a profit. Okay, so I will first explain a very simple folklore protocol. So we actually have something concrete in mind. And then I'll elaborate on the game theoretic notions again. So here we have 4 cryptographers, and they're trying to elect the next crypto PC chair. I mean, PC chair, of course, is a lot of work. But let's imagine somehow all of them are eager to you know, have the opportunity to serve the community. So they all want to get elected. And here's how the protocol works, right? So essentially, we pair them up. Every pair will deal with each other. They play Blum's protocol, elect a winner. The winner survives to the next round. And then the 2 winners will duel again and elect the final winner. So if there are n players, you can do it in a tree-like fashion, and it will take log n rounds. So actually, later in the talk, we are going to focus on improving the round complexity. Okay. So at this moment, we can kind of try to understand what fairness property, this very natural protocol, the tournament tree protocol, can achieve. So first, if you think about it, this tournament tree protocol actually achieves a very strong notion of game theoretic fairness, in the sense that no coalition, like no matter how large the coalition is, cannot benefit itself. Because like the only thing you can do is just abort, because this is a commit open protocol, right? There's basically nothing else you can do. You can abort, but in that case, you just forfeit. So there's no way to deviate to benefit yourself. And also, we also need this, we also have a second property, which is any coalition cannot harm the honest player, cannot harm actually any honest individual, because it's for the same reason, right? The only thing I can do is abort, but that just hurts me and harms, that just hurts me and benefits the opponent. So the second property is also important. For example, if I'm providing, let's say, verifiable computation service to a smart contract in exchange for rewards, it's in my interest to monopolize the ecosystem. So maybe, you know, in the short term, I want to drive away all the competition and like make all the smaller players leave. And, you know, maybe in the short term, it might cost me something to do that, but I'm still interested in like harming, let's say, a single individual. Okay, so if a coalition can harm individual players, it will also create this incentive, like for these smaller players to enter the system. Okay, so now the nice thing here is that, again, honest behavior is an equilibrium. Like if I join the system and I see everyone else is behaving honestly, then my best response is just to play honest. Such a system incentivizes everyone to behave honestly. So we say it's incentive compatible. And essentially, no matter what your goal is, like you can be selfish and profit seeking, you can be malicious and just trying to harm other people, like maybe trying to monopolize the system. You can be paranoid and trying to defend yourself against the worst possible scenario. Like no matter what your goal is, you always want to play honestly. So this is actually something very nice for like these decentralized blockchain type of applications. Okay. So now we know that game theoretically fair leader election is possible in log n rounds with the tournament tree protocol. The interesting question is, can we achieve the same in little o log n rounds? Can we asymptotically improve the round complexity? And again, remember, we are dealing with corrupt majority. And also going forward, because like game theoretically fair is a mouthful, right? Going forward, whenever I say fair, by default, I mean game theoretically fair. Okay, so to answer this question, I mean, of course, we've got to start with some naive ideas. The first thing we want to try is just take the tournament tree protocol and compress it to rounds, right? So in the tournament tree protocol, you do multiple rounds of commit and open. So why don't we just commit everything up front and open everything in the second round? Well, the point is like, this doesn't work. For example, imagine in this case, Shafi and Alessandro are corrupted, like they're in the coalition. And here's the definitive winning strategy. So let's say Shafi commits to 0-0 and Alessandro commits to 1-1. And then they can look at the honest players opening and decide that one of them will abort. And they'll pick the right one to abort such that the other one will definitively win. Okay, so this very naive idea doesn't work. And let me now talk about our results. So I'll first talk about the results at a high level, and then I'll try to help you interpret the results, and then I'll go into the construction. So first, we proved that if we impose too strong a restriction on the style of the protocol, then there's a log and lower bound. Like in some sense, tournament tree protocol, like it is the best you can do if you restrict yourself to protocols that are in some sense very similar to tournament tree. And what do I mean by tournament, very similar to tournament tree? Like remember in the tournament tree protocol, like you do multiple rounds of commits and then immediately open in the next round. So if you are working with this restriction, then there's nothing much you can do. Like log n is the best. So I want you to think of this lower bound as like sanity check for when we design these protocols. So this is not a deal breaker, right? So like who says we have to restrict ourselves to this very restrictive model?
Elaine,
and yes.
Can I ask, why can't we just like commit, like do one round, but commit a number modulo the number of participants?
And the same thing will, the same thing can break the fairness. Like let's say I can, the point is I can look at the honest players' coins and decide what I want to commit. So it's not like simultaneous or atomic. It's like, you know, you post something to the blockchain and I already see your message and then I can decide what message I want to post. So in the cryptography literature, this is called the Russian model. And it also kind of very well captures like the model you would actually have like in the blockchain setting. Like all the miners, like the network relays, they already see the message you want to post before like deciding their own message. Like let's say, oh, so I guess, I mean, the point is like after you open, I can decide whether to open mine. Like you control a bunch of players, right? So everyone first commit and then the honest players open and I can decide which of my own players to abort and maybe the rest open. So in this way, I can bias the outcome.
Yeah, like I think that's in the binary case, there was only one bias, which is the other person wins. In the multi-person case, you can change among the others who win, and that's a violation.
Yes.
Right? Yeah.
Yes.
Okay. Great. Thank you.
So right. So that's a very good strawman example too. Okay. Yeah. So now our upper bound. So we show that if you are willing to relax the fairness to approximate notion of fairness, I'll explain this in a little bit. And moreover, if you are willing to assume standard cryptographic assumptions, then we can actually achieve log n rounds, right? So in comparison with the tournament tree protocol, this is an exponential improvement. So I'll elaborate on two things. One is what is approximate fairness, and the other is like what cryptographic assumption we need. Okay. So this is what I want to focus on in this talk. So first, what do I mean by approximate fairness here? So I have a notion of epsilon fairness, and you may remember from the last slide, we can achieve little o1. It's actually also on this slide, we achieve little o1 fairness. So epsilon equal to little o1. So a protocol is said to be epsilon fair if the following two things hold. So first, we want to make sure that no polynomially bounded coalition can increase its expected utility by more than epsilon. And second, we want to make sure that no polynomial time coalition that contains almost all the players. Like it can control up to 1 minus epsilon fraction of the players. Even such large coalitions cannot reduce any honest individual's expected utility by more than epsilon. Okay, so there are a couple subtleties I want to explain. One is in the first notion, our result actually extends to coalitions of arbitrary sizes, right? Even like all but one coalition, and we don't have this 1 minus epsilon restriction. And this is because actually for the first notion, it's actually kind of trivial to satisfy when you have a really large coalition. So let's say you control n minus 1 players. And like even normally, if you play honestly, your utility is very close to 1 already. And no matter how you deviate, you can only increase your utility to at most 1, right? So like the relative increase is very little just by problem definition. And this is not true for the second notion. And that's why like in our results, we have a restriction on the coalition size, which is 1 minus epsilon for the second notion. Okay. We don't know how to actually achieve all but 1 for the second notion. So it's an open question. So that's the first subtlety. Yes, question?
So the protocol does not depend on epsilon then?
The protocol needs to know epsilon. Epsilon is a parameter of the protocol.
Okay, so, okay, fine.
So I'll give a more parameterized version of the statement later, and you'll see how to parameterize it, depending on how much fairness you want. Okay. So in this talk, I just want you to assume epsilon is 1%, even though we prove something stronger. I mean, this is just for simplicity in the talk. So I think I already alluded at this. So our notion, approximate notion is multiplicative. So in some sense, like let's say the second notion is saying the expected honest utility has to be at least 1 minus epsilon over n. Because if you play honestly, your utility is 1 over n, right? Because the winner, let's say, gets 1 utility 1. So it cannot be worse than 1 minus epsilon over n. And this multiplicative notion is more meaningful than additive in a lot of these practical applications. Like for example, let's say in the blockchain setting, oftentimes we play these games repeatedly, and like the absolute value of the utility like is not very meaningful, and that's why we go for this multiplicative version. Okay, so again, our philosophy here is to have incentive compatibility. We want the honest behavior to be an equilibrium in the sense that if everyone else is behaving honestly, then it makes very little sense for me to deviate. Like maybe I can do just a little bit better by deviating, but the relative gain is like so small, like maybe it's not worth the risk I'm taking. Like I can be caught, I can be exposed, right? So in this sense, it's incentive compatible. Okay, so this is something I won't have time. I'll defer this to the very end of the talk. Most of the talk, I'll stick with these simple notions, but actually we prove something stronger in our paper called sequential fairness. I'll just like spend one slide at the end talking about the sequential notion. And this is related to what Alessandro was asking. We actually prove a parameterized version of the theorem. And essentially we show if your protocol is R rounds, then we can achieve, roughly speaking, 2 to the minus R fairness. And this holds for any R greater than some constant times log n. Like, I mean, if your R is log n rounds, you might as well just use like the tournament tree protocol. So it's only kind of meaningful for like log n to log n. Okay. So for the cryptographers in the audience who might care, like it's actually quite interesting when we compare with approximate strong fairness, because like for strong fairness, we know if you have an R round protocol, like in the correct majority setting, you cannot hope for more than 1 over R fairness. So we actually have a much sharper approximation factor here. Okay. So our techniques are also quite interesting. At very, very high level, we use extractors and honest majority MPC, multi-party computation, to get this result. And you should be surprised here because I just said this is a correct majority setting. So how can we actually make use of honest majority MPC, right? Like why would honest majority MPC give any meaningful guarantee? But you'll see in a little bit.
So Elaine, a question. Your lower bound that you mentioned earlier was specifically in the ideal commit and reveal model. Does that mean that in principle, there could be still some protocol that for computationally bounded parties achieves just perfect fairness?
So first, it's actually in the ideal commit and immediately reveal model. It's like you're committing this round, you reveal in the next round, and you repeat like the tournament tree protocol. And then I basically, if you are computationally bounded setting, if you are using commitment only like not in any like other non-black box way, then I think that the lower bound would carry over. Like unless you are doing something like, imaginative with your commitments. Like if you're just using it as an ideal commitment, like if your protocol, that is to say, if the commitment can't be replaced with an ideal commitment, then you are subject to the same lower bound.
Okay, but it is, I don't know if it's possible or not, but it may be possible in principle to have a protocol where there is no trade-off between the number of rounds and the quality of the fairness.
Oh yeah, our low bound only holds for like perfect fairness in the ideal model. So we don't know about proximate. So like we make actually our protocol, if you look at it in comparison with the lower bound, we are assuming a couple more things. One is approximate, and the other is we are making more assumptions than just commitment. We are using honest majority, constant round honest majority. Actually, we only need log n round, log n round honest majority MPC. And then we are using commitment, but not in an immediately open model. We commit, and then it's opened a few rounds later. So we actually don't know which of these are needed, but at least a subset of these are needed to get this result.
So there is like an open question to close things between the two.
Yeah. So to understand how do you reduce the assumptions needed to get the upper bound is interesting. I mean, again, I think the lower bound is more of a sanity check. And the only reason we had it is because in the beginning, we were trying in that model and we soon realized like, it's not possible. I mean, the proof of the lower bound is like pretty technical, but it was like how we arrived at this conclusion, essentially.
Great, thanks for clarification.
Okay, yeah, thanks for the question. Okay, so now let's actually dive into technical. I'll start with the Strongman scheme. The Strongman scheme relies on the random oracle. So don't be alarmed because I'm going to just get rid of the random oracle in the end. And furthermore, the Strongman scheme doesn't satisfy our fairness requirement, but we'll fix them too. Okay. So here's the idea. The very high level idea is we start with n players. We first downsample to some polylog size committee. And then from the polylog size committee, we elect a winner. So the second part we know how to solve. We just run the tournament tree protocol. And because the committee is polylog size, the tournament tree protocol now takes log n rounds. So the first part, we don't know how to solve yet. And let's think about how to get the first part. So this approach is actually inspired by proof of stake protocols. So again, here we are trying to down select to a polylog size committee, right? And the idea here is for everyone to post a bit to the blockchain. I toss a random coin, I post it to the blockchain. We take the concatenation of everyone's bits and we feed it into a random oracle. And then the random oracle gives a polylog size committee. So if you haven't heard of the term random oracle before, you can just think of it as a completely random function. If you make a fresh query, it gives you a completely random string. If you make the same query as before, it gives you the same answer as before. So if anyone aborts, we'll assume their bit is 0. Okay. So let's think about what this protocol gives us. Imagine the red players, they form a coalition. And of course, again, the coalition can look at the honest players' coins and then decide their own coins. And of course, it's in their advantage because they want to try different combinations of their coins and pick the one that works the best for them. And to maximize your utility, essentially, what you should do is to increase your representation in the committee, right? Include as many of your players as possible in the committee, because the committee will run the tournament tree protocol, and the tournament tree protocol, you can think of it as like kind of ideal. Okay, so that's the coalition's objective. Fortunately, we can prove that, let's say the entire universe has 99% red. And no matter what the adversary does, as long as the adversary is, the coalition is computationally bounded, the committee has to be, like, roughly speaking, 99% corrupt as well. Like, it's a very good representation of the overall population. And the proof is actually not too difficult. Like, first, we are going to, look at a fixed random oracle query. And by taking a Chernoff bound, we can show that for a fixed random oracle query, it's going to select a committee that's good. Good means, let's say, roughly 99% corrupt, and bad means more than 99.1% corrupt. Okay, so the probability that the committee is bad is negligibly small. And then remember, we are going to assume the adversary is computationally bounded, so it can make at most polynomially many random oracle queries. So you can just take a union bound over the polynomial factor, and you get this guarantee. Okay. So just to quickly recap, as I said, we have good news and bad news. Like, the good news is that we can prove that large coalitions, like even 99% coalitions, cannot benefit itself noticeably, right? So, like, remember this Chernoff bound proof holds for any constant fraction coalition. It can be 1%, it can be 99%, it holds as long as it's constant fraction. But there are a couple flaws with this naive solution. We'll look at them one by one. The first flaw is that a large coalition can harm a single individual. And at a very high level, like, this Chernoff type bound gives you a statistical guarantee about the population. It doesn't give any meaningful guarantee about any single individual, right? So, like, if you're a large coalition, you want to harm some individual, like, what would you do? You can look at the honest coins and then try different combinations of your own coins and make sure this user is excluded from the committee. And you can achieve this with very high probability. Okay, so the second drawback is a small coalition can actually benefit itself significantly. So at first sight, this is counterintuitive again, because I just said large coalition cannot benefit itself noticeably. But now I'm saying, like, it's harder to defend against small coalition, right? So why is this the case? And this again has to do with the notion being multiplicative, because, like, for the large coalition, like, its utility, even if it plays honestly, like, it's already very close to 1. But whereas for, like, a small coalition, let's say a single individual, like, my normal utility would be 1 over n. So even if I can just increase a tiny bit, let's say by 1 over n, I'm already doing twice as better, right? So how can small coalition benefit itself? I mean, it's like the same kind of attack. It can look at honest coins and decide the best coin for herself. And because it can try both values 0 and 1, like, you can do a back of envelope calculation. I can do, like, basically twice better than if I played honestly, right? So here, anything that's more than 1 plus epsilon is considered significant. Okay. So we're just going to try to overcome these problems one by one. Let's first think about how to solve the first problem, that is, a large coalition can harm a single individual. So the reason why the large coalition can harm an individual is because it can choose its coins to exclude that person, right? And to do that, it needs to know the player's ID. So what if we just, like, hide all the players' IDs? And then it wouldn't know who to target. So the idea is the following. Everyone's going to pick a random virtual ID, and they're going to keep the random virtual ID secret. And the virtual ID is, like, really what's being elected by the random oracle. Okay, so you commit to your random ID, put in envelope, and now you do this random oracle-based protocol. But the random oracle is, as I said, is selecting virtual IDs rather than real player IDs. So once you've selected the virtual IDs, you open this commitment, and now you know the reverse mapping. You can map back to the actual player IDs, and then from this committee, you select a winner. So there is actually a subtlety here that would break things. Like, because if you think about it, the correct player, the coalition player knows its own virtual ID, right? So one attack it can perform is that the coalition can have assign everyone the same virtual ID. So we all choose the same virtual ID, and then we choose our coins such that this specific virtual ID is included in the committee, and in this way we all get selected. And that's pretty bad. And that's why we need the following modification to the protocol, which is to say the player is only committee member if first its virtual ID is selected by the random oracle, and second, you're the only one who selects that virtual ID. There's no collision with other players. So it turns out something like this would work. I mean, it's not exactly with the parameters I show. Like, we actually need the virtual ID space to be a little bit larger. It needs to be n times polylog n to have small collision probability. I won't go into the proof. So this fixes the first problem, but it doesn't fix the second problem, right? The small coalition can still benefit itself because the small player, the individual player knows its own virtual ID. It can still carefully choose its coin to help itself. So how can we solve the second problem? Okay, so let's try to solve the second problem now. And in fact, I've already given away the solution at the beginning of the talk. I said there's going to be an honest majority NPC, and here's where it's going to get used. So the idea is we want to make sure the small coalition or the individual player doesn't know its virtual ID either. And how can you achieve that? So let's say the virtual ID contains two parts. Like, the first part is this unmasked virtual ID, which is what you select. And then imagine everyone jointly selects a mask permutation. So you're going to apply the mask permutation to the unmasked virtual ID to get your final virtual ID. This is kind of like XORing the two, right? Just in a different format. Okay, and how to select this mask permutation? I mean, this is just where we use the honest majority NPC. We commit to this mask permutation up front, and we open it at the end. Okay, so in this way, if you are a small coalition, right, in this case, the coalition has two red players, they cannot predict their virtual ID because they don't know the mask permutation, so they don't know which virtual IDs to help. But if you control a very large coalition, let's say 99%, then you control the NPC, because the NPC only secures against like minority players. So in this case, you can completely corrupt the NPC, you can control the outcome, but it doesn't matter because for large coalition, the first part of the construction gives security. So that's the idea. Okay. So essentially, I've described like how to overcome these two problems, but there's only one question left. I promise we are going to get rid of the random oracle, and we'll do that. So before that, are there any questions at this point about the first part of the solution? Okay, so how can we get rid of the random oracle? So the high-level idea is we are going to replace the random oracle with a combinatorial object called a sampler, which is equivalent to a seeded extractor. So you won't have to understand what an extractor is to understand the scheme. I mean, of course, it's also not that simple. Like, it's not just replacing the random oracle with sampler and you're done. That won't work. We'll need some extra tools. So in this picture, we have a sampler, right? You can think of it as a bipartite expander graph. The graph has very good randomness-like properties. Each vertex on the left can be identified by a bit string. And we'll think of the vertices on the right as the end players. So basically, every vertex on the left selects D players. So the degree of the vertex, the degree of every left vertex is exactly D. So it's a D regular. I mean, for the vertices on the left, it's D regular. Okay. So here's a strawman idea. Let's say the players, they jointly select a vertex on the left, right? They each post a bit onto the blockchain. We concatenate all their bits. It selects a left vertex, and then the left vertex will select a size D committee. Okay. So we can try to analyze the scheme. So in this example, imagine the first 2 bits are contributed by the honest player, so they're in blue, and the last 4 bits are red because they're contributed by the coalition. The proof is a combinatorial argument. And one thing that's worth mentioning is, like earlier when we relied on the random oracle in the proof, we relied on the fact that the adversary can only make polynomially many random oracle queries. But here the argument is of a different nature. It's like a combinatorial argument. It doesn't depend on the computational bound on the adversary. Okay, so here's roughly the way the argument works. I'm not going to go into the parameter, the details of the parameter. So at a very high level, suppose we fix a coalition, and if a left vertex selects a bad committee, right? So a bad committee is more than 99.1% correct. So if it selects a bad committee, we say this left vertex is bad, and we put a cross on it. And in this bipartite graph, as I said, it's called a sampler. It gives very good random sampling type of properties. Essentially, no matter how you choose your 99% coalition, the number of bad vertices on the left is very small. Okay. So in fact, the number of bad points are so rare, such that essentially for many of these honest coin choices, they cannot be denied. So maybe a little bit more precisely, no matter how the adversary chooses the 99% coalition, the bad points on the left are so rare such that almost all choices of honest coins cannot be denied. And here, what does it mean to be like cannot be denied? We say that a set of honest coins cannot be denied if there just does not exist a coalition choice of coins that can lead to a bad outcome, that leads to a bad point on the left. So it doesn't matter even if the coalition is unbounded, because like there's no way for it to choose these red numbers for the point to be bad. Okay, so in this case, in this sense, if the honest players just pick random coins, chances are, no matter how the adversarial coalition chooses, we are in good shape. Okay. So unfortunately, this is very nice, but the parameters actually don't work out, and I'm going to explain, and I'll explain how to fix it. So essentially, we want the committee to be polylog size, right? So let's just say log to the 9. So D is the degree of each left vertex. It's also the committee size.
Elaine, sorry to jump in. Just a reminder about the time, if you can maybe a few minutes.
Okay, yeah, I mean, this is coming to the end. So maybe I'll skip the calculation, but the point is, like, if we want a polylog size committee, we can show that, like, you want to start with polylog players, like roughly speaking, log cube players. You cannot start with n players, because otherwise there's just like too many combinations the adversary can choose. Okay, so let me kind of skip this calculation. And so it seems like we haven't made any progress, because, like, what we need here is to be able to select a preliminary committee that's log cube size, right? So we're back to the same problem. Well, it turns out that it's actually more subtle, because, like, in fact, we are not back to the same problem. And the key idea here is that we are going to use the preliminary committee, this log cube size preliminary committee, to select a final committee among the entire universe of n players, not just among the preliminary committee. So the preliminary committee's job is to run a protocol like the random oracle kind of protocol before, but now replacing with sampler, to select a final committee. And the final committee is basically everyone is a candidate, not just the preliminary committee. Okay, and then from the final committee, we are going to run the tournament tree protocol to select a winner. So in fact, it turns out for this, because of this key observation, we only need the preliminary committee to satisfy a weaker property. In other words, we only needed to like have enough honest players in the preliminary committee. And we don't care about coalition harming an individual or a small coalition benefiting itself, like for this preliminary committee. We just need like some statistical property over the population. Okay, so fortunately, if we just want this weaker guarantee, there is actually a solution, right? We can run a single iteration of Feiger's famous lattice beam protocol. So I won't go into the lattice beam protocol, but just believe me that it works. And then once we select down to this polylog size preliminary committee that's guaranteed to be 1% honest, we can then run this random oracle kind of protocol we've seen, right, to select a final committee. But now we are not going to use a random oracle, we are going to use a sampler instead. Okay, so remember, we are still going to use the same tricks as before, like we are going to use the virtual ID trick, and we are going to use the honest majority MPC in the second step to defend against the attacks we've seen. So that's kind of the whole protocol. I'll defer to the paper for formal definition, description of the protocol and proofs. So I'll conclude, but I want to just say a few quick words about the stronger notion, the sequential fairness notion we actually prove in the paper. So I've actually cheated a little so far. Like the definition I told you is not always incentive compatible. Let's take one aspect of the definition, for example, basically the coalition cannot benefit itself by more than epsilon. I mean, the problem is like when epsilon is not a negligible function, there could be a bad event that happens with small but non-negligible probability, let's say epsilon over 2 probability. And if this bad event happens, you always want to deviate. Like, let's say the bad event is the coalition steals Jinxi's password. If I steal your password, I might as well crack your Bitcoin account and steal all your Bitcoins rather than following the protocol. But when we take the expected utility, this bad event gets averaged out because it happens with very small probability, right? So in some sense, this basic notion I talked about doesn't rule out some protocols where, with epsilon probability, I might want to deviate. Like there's maybe a small probability bad event that incentivizes me to deviate. So in our paper, we have like a better solution concept that solves this problem, which we call sequential fairness. And I'll defer to the paper for details. And our work is also related to some previous work in the crypto literature, like, for instance, it's related to rational protocol design. Like our non-sequential notion can actually can be proven to be equivalent to a multiplicative variant of this rational protocol design notion. But our sequential notion is stronger. And also we observed that in some earlier papers like Fruit Chain, their approximate fairness notion is like in some sense lacking because it doesn't have this sequential aspect. Okay, so I want to conclude by saying, game theory meets crypto type of work is much needed for the decentralized blockchain space. And in this area, actually, interestingly, industry adoption is way ahead of research. And we need basically new scientific foundations because a lot of the times, like even the formulation of the problem is not clear. We need interdisciplinary work in this area. So it's an exciting area, in my opinion. Thanks.
Thank you, Elaine. And also clap. Are there questions for Elaine? So I have a question. So, for a while, the protocol looked, as we were building it, pretty cute and reasonable. And then it kind of quickly went out of control into much more complex. Would you guess that there is, I don't know, a better protocol from the book that is simpler and maybe gives similar guarantees and maybe is maybe gets better constants or is friendly to deployment, or what's your assessment of this problem?
So for deployment, I've actually thought about it a little bit, and I think this random oracle-based protocol, like some modification of it, might be like, I think it's implementable. Like the question is, how do you realize the honest majority MPC? But the functionality we need here is actually very simple. I think you probably only need like verifiable secret sharing. And then the latter part where we get rid of the random oracle, I think mostly it's like interesting theoretically. And I don't have great ideas how to simplify it yet, but I think it would be very interesting to get simpler constructions without the random oracle. I mean, I think conceptually it's kind of like simple, right? It's like this random oracle based approach, and you just want to replace the random oracle with the sampler. And then, but it's just not all that easy to directly replace it with the sampler. And maybe that's where it got a little complicated. We have to do this two-phase approach, like preliminary committee, and then final committee, and then tournament tree.
Yeah. Cool, thanks. So maybe since we're running a little bit late, I would like to encourage everyone, if they want, especially the speakers, if they want to socialize or ask more questions to the speakers, there's a link I just put in chat for socializing. We're going to take a 1 hour break, so we're going to sort of resume for the 2 afternoon talks at noon California time, but it's a little over an hour. So yeah, thanks again for both speakers.
So the link is the same as the one sent in the email, or it's a different one?
Yeah,
it's the same. Okay.
Throughout the workshop. Yeah.
Sounds good. Yeah.
All right. See you later. Yeah, bye-bye.
See you.